the U value. The U value is the inverse of the R value. Using the U value is the correct way to view an average of systems, or what some people call the whole building U value. Maybe to some people that didn't answer, this might seem like it's getting complicated, but it's quite simple. If we look at the same options from the previous slide, but in terms of U value, option B, where we only add an additional R2 of insulation, greatly outperforms option A. Remember, U value, you want the low number. So what's the point I'm trying to make? Am I just trying to do a bunch of math? Not really. The point I'm trying to make is that the areas we should focus on for existing buildings are the areas that are already performing poorly. Increasing the thermal efficiency of areas that are already doing okay gives you diminishing returns if you don't take care of the low performing elements first. And so this example is actually based on a real discussion with a project team that I've simplified a lot. You know, I made this 50-50. It wasn't 50-50 on this project, it was close, but this is a simplified version of it. But basically the client was really focused on adding more insulation to an already insulated roof because they wanted to increase the thermal performance of the building. They cared about it. They wanted to have a more energy efficient building. But they didn't want to touch the old existing windows because they weren't really leaking. And when I say leaking, I mean water in this case. And they didn't want to disturb the occupants inside. But we were able to sit down with the client and explain that the real bang for their buck was doing a window project and being able to use modeling tools to show and educate someone on why the hard option is worth it can really change the direction of a project and add value to the decisions that you're making. So let's get right into it. These next two slides are, again, I simplify a lot of these things. It's very high level concepts, but this slide is what I call the low hanging fruit of existing buildings, and the next one will be the high hanging fruit of existing buildings. And I call these things low hanging fruit because these are things that require maintenance and replacement. You know, the roof, you can think of it as a range of maybe every 15 to 30 years. You know, it's not going to be the same for every roof, but you know, it has a lifespan. And the same thing goes for the windows. You know, 30 to 50 years for a window, maybe less, maybe more. And whenever we have the opportunity to replace these things, we want to make the most out of this opportunity because you don't get this chance very often. So when you do have to replace it, you want to make sure you're getting the most bang for your buck out of your roof, insulating it right. And same thing goes for windows. You want a high performance window. Not only will it increase the thermal efficiency, but windows are sometimes very bad. The culprits for air leakage. You know, a lot of air leakage can go through old, low performing windows. And you'll see in case study 2 how important it is to address the air leakage on your building. It's not all just about insulation. And then we get to what I'm calling the high hanging fruit of existing buildings. These areas often don't require change. Sometimes you are choosing to do these things. You can't normally do these options without being very destructive to building occupants. You know, continuous exterior insulation, stud wall insulation. If you choose the right way to go about this, you can also improve the air leakage. And a lot of times other decisions in the project are gonna kick off these types of things. You know, you might have a facade that requires a lot of repairs and you hit that threshold where it no longer makes sense to repair it. You're at a point where you want to replace it. And then you can possibly get one of these improvements into your building. So the next couple slides, I'm going to walk you through a few areas where we can have some different strategies. The first one's simple. You know, this is as basic as it can be. The roof. Let's add more insulation to it if we need to. You might have an old existing roof of 3 inches. Let's bring it up to 5 or 6 inches. The complication here might be flashing heights or mechanical equipment. These are challenges that are relatively easy to overcome. The next one is the windows. You know, like I started with the low-hanging fruit, right? You might have some old wood windows or non-thermally broken aluminum frame windows. Your IGUs might be failed. You might be getting a lot of air leakage through the windows. Whenever you have a new window project, let's pick a high performance window that has a good U value and then address the air leakage around the window. You know, the roof and the windows, eventually they're going to need to be replaced. Let's do it right when we get to it. And then we get into kind of the high-hanging fruit options, the insulation options for your opaque wall assemblies. I show 3. I'm sure there are a combination of many things you can do, but just to keep the conversation going, I chose 3. Interior insulation, recladding, or overcladding. And we're going to look at some of the challenges involved in all 3 of these. Starting with interior insulation, the challenges include, disruption to occupied space. Sometimes in your building, the HVAC and electrical equipment is all on the exterior wall. And, if you add interior insulation, you're going to have to reevaluate those trades and kind of move those to different spots. So that can easily jack up the price if you have all of your equipment on those perimeter walls. And then something we often think about in the Northeast is the increase in freeze thaw at your veneer, at your cladding. Most of us know this, that if you have an uninsulated, let's go with a mass masonry building, right? If you have an uninsulated mass masonry building, the exterior brick probably doesn't see that many freeze thaw cycles. The interior heat works its way through the wall and keeps that wall system relatively warm, or at least above freezing. Once you add insulation to the interior side, you're going to increase the amount of freeze thaw cycles that masonry sees. So it's something to think about, something to test, to make sure you aren't going to cause any negative consequences, but it's doable. Next up would be recladding. Challenges involved with that are the removal and disposal of the existing cladding. This was what I was kind of alluding to earlier, where if you have a repair project, there's some threshold where it no longer makes sense to repair it. You might want to start replacing it. Oftentimes that's where I see something like this being driven. We have some projects in New York City, where lot lines are a consideration. Sometimes you don't think about this, but your wall section gets bigger. If you're in lot line construction, maybe you can't make your wall section any bigger. Aesthetic changes could be a positive thing to some people, but others might want to keep the look of their building, so that could be a challenge. And then there's the scary item, which is abatement potential. Right, we're dealing with a lot of old existing buildings. What is in that wall? It's scary to find out what's in that wall, because abatement can double, triple the price of your project, just like that. But all hope is not lost, because if you have that problem, you could overclad. There's tons of options out there. Overcladding, though, would add load to your structure, so there are limited lightweight options available that you can implement without having to worry about upgrading your structure. You got to think about the new support required for your windows and other features. Your windows are going to be moving further out in your wall because you want to keep that thermal break aligned with your cavity wall insulation. So you may require new support for the windows. With moving that window out, if you have narrow, small windows, your sight lines may be reduced by the deeper, rough opening. If you have a small window, it might start feeling like a window well more than a regular window that you might have. And then again, lot line considerations, even more so in this one, because you're really just adding to the wall. And there are many things to consider when you start to think about these 3 options. I've listed a few of the main concerns or things that I've encountered on past projects, but for every project, it's different. So a lot of times it depends on your specific case. So you really have to dive into it on each project specific option. A lot's going on this slide. This is a sneak peek at the end goal. How do we evaluate all these options and combinations? Well, we try to get to something that looks like this. It has a lot of information on it, but it's the information that you want and the information that you need to determine what option is best for you. And Tat is going to jump in now and kind of walk you through how you can figure out which option is best for you by using energy modeling. And he's going to run us through case study 1, which is a university dormitory. So Tat, I'm hoping you're on the line.
Yes, I am. Can you hear me okay, Luke?
Yeah, I may talk a little loud, but or maybe my volume is down.
Sure.
Yeah, you're good.
Okay, I'll talk softer then. Thank you, Luke, and thank you, Sarah, for having us for the presentation today. So I'm going to talk about case study 1. Next slide, please, Luke. Next slide. Yeah. This building is a dormitory in the Boston area. Oh, go back up. Look, go back to the last slide.
Back one? All right, there might be some lag between us.
Okay, yeah. There you go. So for this project, we are, the scope is to review the envelope, the roof, the window, and the brick masonry, see what kind of condition they're in and what kind of renovation option. And I want to emphasize this project was an early design, conceptual level type of a project. Next slide, please. So in this slide, the picture is the floor plan of the building that we're talking about. The main part of the building, which is the elongated horizontal part, is a 4-story main building with about 34,000 square feet. And I'll get to that 2 numbers in several slides later. So we're in Boston. So the climate zone is 5A. The existing wood right now is about R15, and the wall is uninsulated, so it's about R3. The windows are pretty old, at 30 years, and a single pane window. Next slide, please. So when we do building energy modeling, there's a lot of different components going into the modeling part. You have to worry about geometry to model the building, the envelope, and the weather data, HVAC system, lighting, truck load, the schedule, occupancy schedule, or the HVAC schedule, lighting schedule. So there's a lot going on right there. Next. So it can be quite complicated, especially for the project that we're talking about is an early design. So what if we can simplify it? What if we can get with the first tuple? This is possible because, like I mentioned, the case study 1 is an early design project. They just want really quick, rough number to understand what kind of option they should investigate a little bit more. Next slide, please. So we can do this because DOE, Department of Energy, actually has these 14 prototype buildings that's available to use. And these 14 types meant to represent 70% of the building stock in the United States and range from high-rise apartment, fast food chain, warehouse, to hospital. Next. And for our particular case study 1, the mid-rise apartment actually fit really well. Next slide, please. So the mid-rise apartment, the prototypical DOE building, is the total square footage is 33,000. Remember, before we looked at the main floor for that building was about 34,000. The window fashion, the window to wall ratio is 20% for the prototype building, and in this dormitory, it's about 23%, so it's pretty similar, and has the same number of floors for the main part of the building. So It's actually quite similar. So we were able to try to use the prototype building so that we don't have to model the building from scratch. We can just substitute some key elements, such as, for example, the prototype building use a Buffalo weather data, and we're to swap it with Boston Logan. The prototype has R30, we swap it to R15, R17 to R3, and the window for the prototype is double pane, and for our building, we're to swap it to a single pane window. Next slide, please. And once we swap all these elements, we have a model without building from scratch, and then we can simulate different type of cases, and we propose 20 cases. The first 5 cases is the same building, R15 roof, R3 wall, with case 1 the single painted, so existing structure building. And then case 2 to 5 is double, triple pane, or double, triple low E coating. Case 6 to 10 is the same 5 window configuration, but with upgraded roof to R30. And case 11 to 15 is upgrading the wall from R3 to R6. And the last 5 cases is upgrading both the roof and the wall. Next slide, please. So when we simulate energy simulation, one thing I would like to do is we want to plot the energy usage throughout the year from January to December. What are you looking at? The upper graph is the gas usage, so related to heating, and the lower graph is related to cooling. And I simulated the first 10 case studies from 1 to 10. And this is a good sanity check to see if our model is running properly, because if you look at the heating part, you can see that in the summer season, we're not using any heating energy, which makes sense. So that's great. And if we look at one closer in March, what you're seeing right now in the close-up window is a 5-day worth of hourly data. The peak are usually midday, and the valleys at the midnight time frame. And next slide, please. So the hourly data plot is really useful. Next slide, please. So the hourly data was really useful, but it was hard to interpret. So so to summarize, we want to get the annual usage data. And what you're looking at right now is 2 different graphs, the heating and the cooling, for the first 5 cases for different window configuration. Case 1 is a single painted, and then 2 and 3 is double, triple, and then case 4 and 5 are the low E coating. What you see is different bar. You can see that with a double painted window, we can reduce about 24%. Triple pane reduce a little bit more, 27. And then case 4 and 5, the heating actually go back up a little bit. Next, please. So my question to the group right now is, why do you think buildings in the case 4 and 5 actually consume more heating energy? And we have the 4 options there. I'm going to take about 40 seconds for you to think about it, and just type in the chat window option 1 to 4 that you think is appropriate. Okay, I start seeing some numbers trickling in. It seems like that's really consistent. Okay, I think all the numbers are coming in the same number. And it's saying number 3, which is the low E coating, which actually will block more solar heat gain in the winter time. Yes, exactly. This is correct. So good job. So for heating purposes, low E may not be the best option because they actually block more solar heating coming in. But for the winter time, and when we look at the cooling side, you can see that with the low E coating actually can improve your performance by another 20%. So low E is great for summertime, but not winter time. And for this particular dormitory, they actually don't have air conditioning. they only have heating. So for the next data graph, we're just going to focus on the heating part. Next slide, please. So now we get to the busy part, all the 20 cases. So figure 1 is just what we saw, case 1 to 5. Figure 2 is same thing with case number 1 to 5, but we actually upgrade the roof from R15 to R30. And you can see the 5 bars have the same shape. It goes down and then go back up in the last 2 cases. But overall, you can see a 12% reduction. And if we look at figure 3, which is upgrading the wall from R3 to R6, you can see a 24% increase. This is actually a good example of what Luke just talked about at the beginning when he gave you the option A and B with the to upgrade a lower R value, I think it was R2 to R4, and then upgrade a roof that it was like R30 to R50. So in our case right here, our wall, which is only R3 because it's uninsulated, by upgrading the wall, even though we're just jumping it from R3 to R6, we actually see a bigger reduction in energy saving, 24%, compared to increasing the roof insulation from R15 to R30. And if we look at figure 4, we also combine the both wall and roof insulation. We can increase the efficiency about 36%. Next slide, please. So the figure just now was really interesting for the university. We actually spent a lot of time looking at it because they want to understand what different options going to get them, what kind of saving. Again, the saving are in terms of percentage because this is a simplified model without actually modeling these particular dormitories, but the percentage should carry for early design part. So the university owner, they have limited money. They're trying to figure out what to spend. And they decide to spend on the window that is 20%, that has 20% saving. And also because the window is pretty old, at 30-year-old. The roof is only 12% saving, so they did not pursue it. And also the roof, after inspection, they still have a few years of lifespan in it. The wall, even though it could save a lot more energy, 24%, it was a lot more expensive to actually renovate the wall, so they also did not pursue that option. And the walls are, despite insulated, is not in not that bad of shape. Next slide. So once that the university narrowed down to the window only, they want to figure out, do they want to do double pane or triple pane, or do they want to do also low E coating? So we did a simple payback study for them. We do not know how much heating this particular dormitory used because the university has a centralized heating, and they don't break it down to this particular building. So we assume some basic number, 50,000 annual cost. We don't know if that's true, but that is to us that's like a lower bound how much this building may use. And the estimate, the 1.4 million to 1.8 million, the actual cost with those 4 window types. So with the energy saving from 24% to 70%, it translates into about 12,000 to 8,000 annual saving. And if factor in the 1.4 million, it's going to take them 100 to 200 years to actually for the payback period. So next please. So we also look at what if the payback period is more in line with the lifespan of the window, which is 15 to 30 years. So for us to get that number, we actually need to bump the annual heating cost to $375,000, which we know is not true. The university is not spending that much money for that building, for the heating cost. But that gave them a sense of idea about what kind of range of payback period they can look. So after looking at this, they know that they're investing on the window not for the payback period, but more for because the window is pretty old and they should be upgrading them soon. And looking at the payback period, triple pane and double pane is still high a lot of years, and at the end they decided they're just going to go with double pane with low E. Even the low E is going to give them comfort in the summertime, despite the fact that they don't have air conditioning. They still care about comfort for the student. And down the line, they're thinking about putting air conditioning, but that is fine in the future. Next slide, please. And I think that concludes my case study 1. So I'm going to pass the ball back to Luke to talk about case study 2.
Thanks, Pat. I'm going to move a little bit more purposefully with my slide changes. Now that I know there's a 5 to 10-second lag behind there, so I apologize in the beginning if I was talking before the slide got to the screen. So case study 2 is going to be a university library. The library is in Western Mass, and the scope was very similar to the previous case study. We reviewed the roof, windows, and brick masonry for that project. Some specifics about this one. The campus had some energy improvement criteria. Well, first off, there were some repairs to be made on this building, and they wanted a minimum of 50 years service life for these repairs. And then the second kind of driver for this project, they wanted to provide, this is a campus-wide goal, a 20% reduction of the building's current energy usage. Once the project gets so big for this particular campus, this is a goal they like to implement. And then the aesthetics needed to be similar to the existing building, you know, as practical as possible. Another thing about this case study is that it was a DCAM project. And for those of you involved in DCAM, they oftentimes require 3 options or 3 levels of repair. So consistently through options 1 through 3, 50-year service life of repairs. It's something they really cared about maintenance-wise with their buildings. And then we had the 20% energy improvement. And they let us know that this is more of a goal rather than a requirement, because they're pretty knowledgeable, and they understand that some buildings it's more feasible to implement energy saving options than others, but they still wanted to see kind of how far they needed to go to meet this goal. So in our 3 options, we wanted to show option 1, which was where you just repair what needs to be repaired and see what the inherent energy upgrades from these repairs were. Then option 2, we implemented what we kind of categorized as low disruption energy upgrades, things that aren't going to really bother the library too much from an occupant standpoint. And then option 3, we threw everything that we could think of at it, just to see is that what's required to get them to 20%? So just different levels to see how close they were to hitting their goal. The next couple slides, again, simplified, boiled down version of the different types of things we were looking at that we could implement on this building. So I think we had 4 cases. I'm gonna take you through each one of these cases. So case 1 and 2 are these lines of windows that run all around the building. This is the existing wall section. We had an aluminum framed, non-thermally broken window. We had this, we call it 2-foot section of Jamb brick, right? This is just mass masonry, no insulation. And then I realized I cut this section off, but if you look over here, there's actually insulation at these piers between the windows. So it does contain some existing cavity insulation. So option 1, which from the beginning, we had a feeling that we really wanted to address this, and in this option, this is included in all 4 options, is replace the windows. We noticed that on the building, there were a lot of what I was calling perpetually wet areas on the brick masonry, and we reviewed this in January or February. And to us, that indicated that there was a lot of air coming out of these windows. And this was higher up on the building, a lot of stack pressure pushing air out of the windows and condensing on the cold brick. So we knew we had a lot of air leakage coming out through these windows. And we saw a lot of, I may have said these were single paned, but they were double paned. It's just everything was fogged and failing. So they're essentially acting as a single pane window. So case 1, replace the windows. Case 2, reconstruct this mass masonry area to include insulation in the cavity to make it continuous from the wall cavity to the thermal break of the window. Then also rebuild a stud wall inside and add insulation to it. So that is case 1. In case 2, case 3, I mentioned before that we had cavity insulation that's already existing. Well, we identified the interior wall as a relatively simple location to put additional insulation. There wasn't any HVAC or electrical equipment up against this exposed concrete wall, so we thought this was one of the lower disruption type of options that we could implement inside. And then option 4 is pretty much a combination of everything, you know, new window, continuous cavity insulation, and interior insulation. And we also bumped up this stud wall a little bit since we were including more insulation on the interior side of this exposed concrete pier. And so these are the 4 cases that we are focusing on for this case study. And I'm going to hand it back over to Tat to go through the modeling strategy implemented for this building. This building was not, I mean, you can see it, it's a fairly tall building. It is not similar to any of the DOE models that were available to us like the previous case study. So we had to go about modeling it in a different way, which Tat will walk you through. Tat, are you on mute, or am I the only one not being able to hear him?
I can't hear you either.
Sorry. Yeah, sorry, I was on mute. And I was making a very good joke with about Luke and praising him, but I guess no one can hear that now. No, don't worry.
Man.
Anyway, Luke, can you go to the next slide?
Sure can.
Yes. While Luke is going, I see that there are comments on the chat room while we're presenting. So I see really good comments, and we'll get to that at the end of the presentation. Do we have the next slide yet? Slide 41.
I'm showing slide 43 right now. Tat, you want to be on slide 41?
Oh, I'm still looking at 40.
Oh, man.
Okay,
Well,
I'm
go back
trying
to 41.
Okay, I see 41 now. Yes, thank you.
It might go to 43 and then back to 41. So let me know.
Got it. All right. Okay, thanks. So we okay. So we like Luke has mentioned, this is a relatively unique building. It has 20-some floor, and also the basement has a relatively large basement with a courtyard in the middle. And not only that, the facade, the triangle column between the windows actually make this is a type of shading, and that would be the model accurately for us to capture the building geometry. And that's why we had this particular model building, where the model from scratch, which is different than the case study 1. So it's significantly more effort, but at the end is for this particular building, you just have to do it this way. So we create a baseline model using the original drawing, local data, utility bills. We also have the envelope model that has run through the option, the case 1, 2, and 3, and the R value related to that. And then we incorporate those different envelope renovation options into our proposed design model, and then we'll compare the energy cost for the baseline and the proposed model. Next slide, please. While we're waiting for it, so in slide 42, what you're going to see is the building in floor plan. You'll see the basement floor plan, which is occupied the lower 1, 2, 4. And then you will see a typical floor plan, which occupy basically from floor C to just right below 27, I believe. and those are the more typical four. And then at the top of the building, there's utility, mechanical area, and then we have a model that's slightly differently. I'm still seeing 41. Luke, are you seeing 40? Oh, okay, now I see 42. Great. I'm glad I was talking about the correct slide. For the thermal zone, we have 8 thermal zone and 22 multiplied block that the figure on the right-hand side somewhat explained. The climate area, this is because we're not using names, so let's just call it Wonderland in Massachusetts, that we actually use on-campus weather station. And the heating and cooling set point are 68 and 72 degrees. Next slide, please, 43. And I'm going to try to remember what 43 is about.
This was your calibration slide.
Yes, great. So while we're waiting for it to show up, I'm going to start talking about it. So for the calibration part, so for this particular building, we have the universities were able to give us the gas and electricity data from July 2018 to June 2019. So 1 year worth of data. So great. Our initial idea is that we're going to calibrate to both the gas, heating energy, and the electricity, so that we can calibrate our model. But very quickly, we realized that we cannot really calibrate the electricity. It turns out, as bullet point 2 say that the library has its own chiller that is also providing cooling for 2 other buildings. So that means the electricity is not just consumption is just not for this building alone. And also we don't have survey data for the lighting load and plot load, so that kind of makes the electricity calibration inaccurate. So then we just focus on the heating part using the steam consumption. Then we focus on the winter months from November to March. If you look at the line graph on the right-hand side, you can see the blue line is the utility bill, and the orange line is our simulated cases. You can see that it's tracking actually pretty well. So one thing we're trying to make it track very well is first we use the local weather station. So that's the local data, weather input data is accurate. And we also have to vary different type of air infiltration. So for this particular building, it's 50 years old. So it's going to start to get quite leaky for air leakage rate. But we do not know what the air leakage rate for the building because we did not do a whole building air leakage test. So we start assuming some value, very leaky building into a more airtight building. And that's the orange line that you can kind of move it up and down. It will move up if you assume a building that's more leaky. And if you assume a building that's more airtight, then the orange line will move down. And at the end, we find out that a 0.4 ACH is actually a good number. And I'll explain what ACH is. Next slide, please.
Ted, do you want me to fill this slide out with all the different graphs since it's
going
so slowly?
Just fill it out so that we don't have to wait. Great, smart. So on the right-hand side, on the left-hand side on the images, you will see that the thermal image of the top of the library. And the thermal image is actually taken early in the morning so that you can see in the cold air in the morning, you can see how the heat is coming through. If you look at the bottom building, you can see that the window frame is actually losing a lot of heat. That's brighter color. And not only then, and that makes sense because of thermal bridge. But what's interesting is you can see that the middle windows are brighter color compared to other windows, even though they probably should have the same thermal bridge. So one of the reasons could be because the middle 2 windows, the wear and tear is greater on the air leakage part, and actually leaking more air compared to the windows on 2 sides. So when we talk about air leakage, the code value is 0.4 CFM, cubic feet per minute, per square feet of exterior wall. And it's described as 75 Pascal pressure differential. So what does 75 Pascal pressure differential mean? That is it means when we talk about air leakage, we have to talk about pressure differential between inside of the building and outside of the building. If the air pressure and the outside and inside are identical, you won't have air leakage. However, if your outside pressure is a lot higher compared to the pressure in the inside, then you have air leaking in, and vice versa. If the internal pressure is higher than outside, then air is leaking out. And 0.4 CFM translate to roughly about 0.1 ACH or 10% air volume change per hour at that 75 Pascal differential. So what it essentially means is every hour for this particular library, which has a volume of 4 million cubic feet, it basically every hour it will leak about 400,000 cubic feet of air. Next slide, please. So what you're looking at is actually the winter energy consumption per year for different cases that we have talked about, case 1 to case 4. If we look at the first case 1, what you see is 5 bars. The darkest blue is the base case with 0.4 ACH. And then we simulate the case 1 with the new window that has a U factor of 0.22 compared to the original window that's 0.7. And if we stay with the same air leakage rate, 0.4, the lighter blue, you will stay 5%. However, when you replace a window, you can anticipate that you actually would improve the air leakage rate, because as the thermal image we have talked about, one of the potential area with a lot of air leakage is the window area. So as we're improving the air leakage, we assume from 0.4 to 0.3 to 0.1 to 0.2 and 0.1 to just kind of get a range of numbers. So it will say from 5% all the way down to 21%. Hit next, please. Actually, look, you can just hit next like 3 more times to get to case 4. Yeah. So case 2 is new window and then new stud wall, and you will say from 10% to 26%. And then if we replace new window and the spray foam is with the on the triangle column area, then we say from 7 to 23%. And case 4 is combining basically case 2 and case 3 together, and you will say somewhere between 12 to 28%. 0.1 ACH maybe it could be a little optimistic, but if we're gonna putting this many type of renovation options, we're confident that maybe we should land somewhere between 0.3 and 0.2. And if we look at case 4, that is still 17 to 23%. And if you remember, for this campus, they have a target of 20% energy consumption. They were happy to see that, but they also wanted to ask about what about in terms of dollar value. So for this particular building, they have the gas consumption, the steam consumption, and also the electricity. And we found out from the university the unit cost for those elements. And turns out this building will use about almost $800,000 per year. That translates to, for case 1, you're saving the 5% become 40,000, and the 21% become 166K. And case 4, now you're saving between 95 and 220K dollars. So great. One thing we don't have for this particular project, because it's very much ongoing compared to case study 1, is we actually don't have the different renovation option, the estimate. We're trying to get a contractor on board, and we're trying to get a quote for those different type of renovation option. And once we have those estimates, then we can update and provide the simple payback period that we have sold before. But that is still much ongoing. So the universities have not made the decision, and they'll make the decision once they have those estimates. And with that, I think that's the last of my slides. And if we hit next, that should be wrapping up.
So I actually have one question. Can you go back one more slide?
Yeah, give it a 15
Sure.
minutes.
Yeah.
So for your percent savings, is that annual, or like what is the time frame?
That's annual. That's the percent saving for the annual heating cost.
Wow, that's a lot.
It's a big building.
It is a big building. It's a 28-story building, and oh, I forgot to mention, and the library is 24/7. So it's a building that uses 800,000 electricity and steam every year. So it's quite a lot.
Does
So
anybody
while
have
we're
any?
waiting for other,
Oh, sorry.
go
I was
ahead.
going to open the floor to any questions, but continue.
Sure. While I'm waiting for other people's questions, I'm going to address some of the comments in the chat area. I see that they mentioned about we have low E coating on the south facade while having low E coating on the northeast and west. That is a valid, good option to do so, especially for building that is in a colder climate. If you're in somewhere in Arizona, then you probably want low E coating all around. One thing about with low E coating is it will actually does change the color of your window. If you're going to have low E coating for the entire southern facade, and that's good, but you don't want to mix and match in the same facade because it may look kind of weird. So a second comment I see from Greta is about energy savings is an important goal, but not the only goal, and about comfortable environment. I completely agree, and that's the reason why the university, for the case study we wanted to go with a low E coating, even though it will increase the heating consumption, and they only have heating for that particular building, but they will worry about comfort in the summertime from the student that may be living there. So yes.
Sorry. That group was very, Greta, it was a great question. And that group was very analytical. They wanted to see every option available, low E or no low E option. So that's why it was on the table to even begin with.
Yeah.
Were these windows operable for the?
They were.
Okay.
There were a lot of different types, but they did have some operable windows.
Yes. And from a building model point of view, we do not like operable windows. It's something that we cannot control.
But everyone else likes
them. So we
them.
assume they're not operable. But from residential point of for residential type space, you do want operable windows. So.
Great.
So can I ask, the bottom line on the low E coating is you recommended to not have it on the south facade in this climate?
I don't know if I would say that for every building. It's one of those classic it depends types of things. You know, I'd really want to focus more on the building before I start picking elevations that have it or don't have it.
So what are the advantages that it excludes the heat you might gain, and therefore it's good to gain heat in the winter. So what about the comfort issue of being close to a cold window? You still feel cold, right?
Right.
So
for our particular, yeah, go for it, Tap.
Okay, so for comfort level related to window, triple pane is where it comes in maybe a factor. Generally speaking, triple pane don't pay for itself if you look at the payback period, because you get a little bit more better in U value, but it's a lot more expensive. One of the figures we're saying that is 1.4 million versus 1.8. So percentage-wise, you're looking at like a 25% increase in cost. However, triple pane window is more comfortable. So if you have floor-to-ceiling window that you want to put people next to it, you may want triple pane window, even though it won't pay back, but at least you make that space along that area to be more comfortable and become a usable space, and that will improve your space utilization in your building.
But if you leave the low E coating on it, then that improves the comfort next to the window too. So if you're talking about
summertime, but not in wintertime.
Yeah, the low E coating doesn't improve comfort in the winter.
So low E coating does two things. It actually does improve a little bit in the U value, so it actually makes it a little bit more insulating, a tiny bit, but it will block a lot of solar heat gain. So that means in the wintertime, If you have low E coating, you're actually not getting that much sun heat coming from the window.
Yeah, so you don't gain the heat, which you would want to in the winter. But if you're sitting next to the window, your body won't radiate out to the outside, so you can be more comfortable.
Yes.
Also,
It could.
And then for our
Depending
particular
how cold you
case, they had their heating right by the window, so that was kind of how they were fighting the condensation issues that you might have with a non-thermally broken window. That's why they didn't have problems with that prior to this renovation.
I had one other question on the and I'll shut up. Triple glazing is there are new, and I'm forgetting in my pea brain what the name of the company is, but there's a company that's producing thin. I guess the trade name of the products is Thin Glass, and it uses a very thin plastic film between the two panes in a regular light of glass to achieve a triple glazed window with very little weight, and you can install it in a regular window. So, I mean, that would get your costs way down.
Do you know what the premium is on that type of glass compared to
No,
traditional? Yeah, I'd be curious with.
All right, well, we have a couple more questions. One of them is for the different cases of ACH improvements for case study 2. How was ACH being improved from 0.4 to 0.1?
That's actually a very good question. And we didn't have too much time, so I kind of glanced over that. I briefly mentioned when you upgrade the window, you will improve your air leakage, because windows, especially windows that are getting 20-some years old, it starts to get quite leaky. The gasket, the weather strip around the window just start deteriorating. And so that's one area that you can improve the air leakage with. And if you're also going to do upgrade on the wall, your walls also leaks air as well. And if you're upgrading the wall and you're putting more insulation, the more barrier between you sandwich between the wall, the more, generally speaking, the more air improvement, that leakage improvement you can get as well.
And these
actually measure.
Yeah.
Go ahead.
Oh, I would just say these numbers would be tighter too if we had whole building air leakage information, which we don't have right now.
So if you go up to one slide, 45, we have a huge caveat at the bottom of the figure saying that if we could do a whole air leakage testing, it would actually calibrate the model even better. But we don't have that option for this. We don't have this option yet. We're trying to convince the university to do air leakage, but it's a 20-some story building, so it's going to be quite expensive.
We have a good idea about what the air leakage is, because that's what we kind of adjusted whenever we were creating our model to get it to match the utility bill. That's how we landed on that 0.4 ACH, is by adjusting this graph until they kind of matched up.
Mm-hmm.
That's the one variable we were missing when developing this.
Okay. Another question, or Greta, did you have something to comment on?
it sounded like you use spray foam insulation for the added insulation, so that's great at air sealing, kind of answering Richard's question.
So where we were rebuilding the wall, we would have had a dedicated air and vapor barrier there,
true.
since we would have had access to it. But you're right, there was a portion of the wall that it was pretty much mass concrete with a little bit of insulation on the outside, and that's where the spray foam would have been to help improve the air barrier there.
Yeah, I see.
Tad, this is for you. Have the new MA Energy or Mass Energy stretch code set a carbon emission threshold for existing buildings? And is that something that's influencing your retrofit strategy?
So there's a two parts to this question, actually more than two parts. So the influencing part is for case study 2 and even case study 1. So most universities these days have their target emission target for 2050. They want to reduce certain amount. So universities do care about carbon emission, and that's why they start asking us to do more energy model for them to understand the impact in terms of energy and carbon emission. The Massachusetts Energy Code does not have a limit on carbon emission. The Boston city is trying to push some type of a carbon emission incentive. It's still in discussion, but for the past couple of years, if you're in Boston area and if your building space is more than, I think, 35,000 square feet, you actually need to report your energy usage, and they have a map. I don't remember the name right now. It starts with a B and ends with a.
Is that the Beardo map, Tat?
Yes, Beardo. Yeah, great, thank you. Yes, if you Google search that, you will actually see a very nice map, and it actually tells what building is using how much energy, and that is the commissioning part, the reporting part, and now they want to take that information and flip it into action. How they're gonna implement a carbon emission. I think they're targeting more energy reduction for this building now that they actually have some data. But that is still very much in discussion right now for Boston.
What was the modeling software used for case one?
So we use, for case one, we use EnergyPlus, which is a DOE free software that you can download. For case 32, we use building energy, sorry, I'm looking at right now. I'm looking at this slide, Design Builder, which also use EnergyPlus as an underlying engine. It just has as a graphic user interface for creating the geometry a little bit easier compared to the latest EnergyPlus program.
Well, thank you so much. I don't believe that there are any other questions. So for those who joined later after the beginning, if you would like a certificate or AIA credits, I ask that you copy and paste the link that I just posted in the chat below. And as far as the Boston Beck future events, the only one that we have up and coming is our February meeting. I believe on the 27th. Well, it's the last Monday of every month at 4 o'clock. So it's the 22nd.
Oh, could I add something? We have a committee organizing a second symposium in honor of WAGD, and we've just gotten we're going to ask for proposals. So we've just gotten our RFP ready, and keep your eyes on the BSA Beck website to hope lots of you will submit. Well, it's not worth my holding it up in front of the camera, but that's coming up, and the date is going to be the 23rd of September this year. We're hoping it will be in person, but we're keeping our minds open to a virtual event.
Great.
So 23rd of September here in Boston.
And I can post that information on our Beck LinkedIn page. So if you guys haven't joined already, please do. I post all of our upcoming meetings as well as, content that we like to share about our industry. So thank you so much, Luke and Tat. I really appreciate it. And if we don't have any, we have one more question. Have you encountered the case when it was fine to keep leaky-ish windows and recommend installing a radiant heating?
I don't think so. But Luke, have you encountered such a case?
No. Sometimes that is an option on the table that almost feels like a throwaway option if we have like a condensation issue at a window. How do you fix that? If you keep the existing window, you got to warm it up. But that requires energy, so we try to stay away from that. We prefer a more passive option, which replace it with a high performance window that isn't going to see that condensation, or there are other creative ways to go about it, but we try to stay away from energy using options like a radiant heating system. Sometimes that's the only option. So you have a historical building where you want to keep a steel framed window but you are having condensation issues. If you take a historic building and turn it into a museum type setting where you need to add humidity, that's just something that resonates in my mind from another presentation that I've watched. You add heat tracing or radiant heating in that case, but those are, I would stay away from that unless there's really specific circumstances that would require it.
Great. All right. Thank you everyone for attending. I appreciate it. And we will see you next month.
Thanks.
Thank you for hosting
you.
the meeting. Thank you for your work.
Thank you.
Great presentation.
Thank you. Bye.